Hello everyone, welcome to today's webinar, Adam's webinar titled Vehicle Dynamics Analysis Using Adam's Car. My name is Yijun Fan and I'm the Product Marketing Manager for System Dynamics. Today we are very glad to welcome Peter Dodd, the Vice President for System Dynamics at MSC Software, to talk a little bit about Adam's Car. After Peter's presentation today, we're going to have a 10 minutes Q&A. So if you have any questions regarding today's presentation or Adam's Car or the general Adams or any suggestions, please type the questions or suggestions down in the Q&A window. We will try to address that either during the Q&A session or following the webinar. Okay, now I'm going to pass the presenter to Pete.
Thank you, Yijun. Hello, everybody, and thank you for taking the time to join us today. I hope you'll find this session informative. We do have a lot of ground to cover, so I'm going to get going straight away. Just one quick note, if you have any difficulty with the visual or the audio, then please drop us a note in the Q&A window. We'll be monitoring those through the presentation, so if there's any issues, we'll catch them as early as possible. All right, so let's get straight into it. Basically, the agenda today is to really talk about the application of MSC Adams in the automotive domain. We want to go over some of the key 2015 new features and functionalities that have been released, and then look ahead to next year. So calendar year 2016, what is it that we plan to make available during that year? So in terms of applications, you know, many people recognize Adams as ride and handling vehicle dynamics application, but it is that, of course, and again, so much more. There are many other departments and groups within our customer base that use it in the powertrain division, for instance, for durability, so loads prediction, loads histories, so on, vehicle safety for advanced vehicle maneuvers and the propensity maybe for a vehicle to get into a dangerous situation. Higher frequency work for NVH, as well as with ride and handling. And then in general drivetrain work, a lot of transmission applications and driveline applications. And then in terms of our customer base, then of course it's many and varied. The product is used around the world. And in fact, when I was looking recently at global vehicle manufacturers by volumes of vehicles produced, it turns out that 44 of the top 50 global manufacturers of vehicles in the world use Adams today. So all of the logos you see on the screen here, and of course many, many more. So let's look at Adams car architecture. This is perhaps looking at things in a slightly different way than typically. This is not looking at features and functions. It's kind of more looking at how our customers use Adams in the workflows that they have today. So of course the fundamental components, the fundamental building blocks would be the pre and post processor and the solver. Excuse me 1 minute, there we go. And then we can add to that a variety of functionalities. And again, we're not looking at features and functions here. We're kind of more looking at how some of our users may be working with the tools. And we'll cover some of those. Then over on the left-hand side, we've got some of the applications, the horizontals, as we would call them. And during the presentation today, you'll see some of these boxes have been highlighted. These are some of the key features that we'll be focusing on. Beginning with parametric modeling. So, what have we been doing in 2015? We've released Adams Machinery Gear. That functionality is now being released in what we call the verticals. So the products Adams Car and Adams Driveline now have access to this new way of representing gears. There's a variety of fidelities offered. But the key here really is trying to save the user time in putting together gear systems very quickly and with high level of accuracy so that we can look at things like backlash and gear rattle very quickly. So you see some typical applications here: differential, obviously, steering systems with rack and pinion gears. Typical use case. So here we have a dual angle hypoid, which is one of the options available for the differential gear. Typical application here in a rear-wheel drive vehicle architecture. We've also done the same thing for the Adams Machinery electric motor. So taking that module and bringing it directly to the car and driveline user. And again, similar to gears, that this provides the user with an easy interface for modeling what is in effect a complicated component, an electric motor. So we've provided four different motor types, specific electric motor types, and it's a wizard-driven environment. So basically, you input some of the key parameters depending upon the type of electric motor and the complexity of the motor that you want to reproduce. And then the electric motor module will put the component together. So here we see the applications of electric steering system. We've also got an auxiliary electric drive on a rear axle here of a vehicle. So occupant and cargo modeling. We've released some different ways really of playing around with passengers, driver passenger locations, cargo locations. So really, again, it's really an ease of use feature. So we make it simple to try out lots of different occupant positions and make it very easy to move these masses around in the vehicle and see what effect they have on the vehicle performance. Dual wheel support, so probably for medium duty pickup trucks and then the commercial vehicle market, the ability to put dual wheels there on the axle and on this suspension test rig. So moving on then and talking about some of the vehicle model libraries that have recently been introduced. So here you'll see a variety of different vehicle architectures, from a subcompact, small passenger vehicle, right the way up to a pickup truck. And the idea here is not just to give the user a vehicle style that looks representative, but also the starting point for the vehicle architecture, the suspension types and the mass and CG location. So it's really just to give you a better starting point for different vehicle styles that you may be modeling. Vehicle event libraries. So the first one here is the static vehicle characteristics. So this is basically what happens, and it's really a model check as much as anything else, but this is what happens as the vehicle settles under its own weight, not a dynamic event, but just coming to a 1G static equilibrium. And then the output here will give total weight, of course, but weight distribution front to rear, CG locations, moments of inertia, and things like that. So this is really just a preliminary check of the health of the model, that it's giving you the kind of results that you'd expect to see. Perhaps the next step would be to do some kind of SPMM. This is the suspension parameter measurement machine. So this is really a reproduction of a kinematics compliance rig. So here the vehicle is being exercised above a set of tire pads, and then the resultant loads, forces and torques are being measured at the tire contact patch. The output of this type of test is very familiar for those people who are used to running a kinematics compliance rig as a real life physical test. So it makes comparison of the analytical model results and what you would see from a test rig very easy. And again, this comes as an available test rig directly for Adam's car, and saves a lot of time for customers who in the past may have built this type of rig themselves. The tandem axle suspension analysis, so TASA. So again, what we have here is the ability to introduce multiple axles. So in this test rig here, for instance, we're showing the ability to tune the suspension system on this multi-axle system here. So again, it comes readily available. The test rig is there, so it's just an ease of use feature for multiple axles commercial vehicle customers. And then looking at some of the solver extensions, so Adams tire models. There's a variety of tire models available to the Adams user that come with the Adams package. You can see them listed here. In addition, of course, we have the F-tire from Cosin, and we've adopted the Cosin tire interface. So this enables us to do more with the F-tire and also to couple with maybe custom tire models that the user may have created or come from somewhere else. So the features that are available now for the F-tire user would be multi-road contact. There's an example of that in the animation screen there, and compensation for belt mass and inertia.
You know the Adams, rigid body dynamics. We've been doing linear flex bodies for a while now, but really that's pretty dated, and for some use cases isn't sufficient. Well, we've introduced a native nonlinear beam formulation as of last year, and we've been enhancing that since. It's based on the ANCF technology, and it's basically you could imagine spring applications for vehicles and leaf springs, coil springs, that sort of thing. We've been enhancing this technology to support those use cases. There are other automotive use cases, cables for even elevator applications that have been of significant interest to get the geometric nonlinear behavior of the system. So the FE part is strictly for geometric nonlinear beam applications, but the important thing to note is that development has been done core to Adams Solver. So it's just another element type within Adams that you can draw on, and so now there's this more. It's an FE-based approach, but it's native to Adams is the important point. But we also realize that there's interest in coupling Adams, and so we've developed an Adams, what we call our ACSI feature. It's Adams co-simulation interface. And you probably heard over the course of the past year about interfacing with Mark. Well, this happens to be an extensible platform that we chose to first mate with Mark. And so we've used Mark as our first technology for coupling, for co-simulation. And we'll talk about the use cases in a minute. But it's extensible, as I said. So we actually have a project right now with the DEM Solutions team out of the UK to interface with EDEM, their discrete element modeling technology for bulk material handling. And so you can imagine off-highway applications and mining and even some consumer applications are particularly good here. And I think Egan has something to say on this technology here.
Yeah, and also if you want to observe the contact between the tire and some of the soil or some of the real high fidelity off-road road type of scenario, we can also enable you to do that. So,
with discrete element model?
Yeah, with Adams and EDEM. That's one of the use cases that we're looking into when we're developing this tool.
That's great. Oh, well, there's a third nonlinear technology. So far we have a native beam element that's useful for many applications. We have this ACSI feature that lends itself to co-simulation. We also want to leverage this Nastran SOL 400 technology that we have in-house. And so what we're doing currently is we are incorporating Nastran SOL 400 technology directly within Adams so that Adams can consume a BDF and that an Adams engineer can run a full simulation that accounts for that high fidelity component, and then thus provides appropriate boundary conditions, and et cetera, et cetera. So these are some pretty significant developments on our part that I want to make you aware of, and I've got a few more slides to describe them a bit more. So with this in mind, the FE part, again, an ANCF, it's actually a hybrid ANCF approach. It uses a geometric exact beam formulation as well. It's something that we developed inside and have published about. So it's, again, useful for those geometrically nonlinear use cases for beams. And springs, in particular, are a target use case with this technology for vehicles. So the workflow is pretty straightforward, and in essence, I won't spend too much time on it, but you can define the center line of your beam element and then basically construct using this little utility in the UI. You can construct your ANCF beam, and then you have nice continuous stress strain as opposed to what you might see with a piecewise continuous M&F or discrete flexible link type approach. We also, on the COSIM interface side with the MARC, Adams can be used to interface with one or more MARC models, and that may be of interest depending, but we do have, the workflow is pretty straightforward. You basically select nodes in each model, and they interface exchanging forces, positions, displacements rather, and then for this particular technology, you post-process separately, or you can bring them together into CEI Insight, for which we have a plugin. So the advantages of that, really, if you're a MARC user, then you realize that modeling a full system in MARC becomes very computationally expensive, and then you don't often have the appropriate boundary conditions. This helps you overcome that by coupling the two technologies, modeling only what you really need in MARC in that particular format, and using Adams to construct the rest of the model and drive the co-simulation, giving you appropriate boundary conditions and still getting you that high fidelity at the component level. And that's something that has been of great interest to many people, including those guys looking at engine mount applications or bushings. So that's something that I think you had mentioned, and so mounts are a target use case for this technology, as are other components. So this is one use case that Volvo allowed us to publish, and they validated their physical test with the simulation of a curb strike event. And they wanted to see when the lower control arm would go plastic and what that behavior, how that would influence the system. And so you can see in here the bushings and the lower control arm are modeled in MARC. The rest of the system is modeled in Adams, and we co-simulate and evaluate the buckling behavior of that lower control arm. And so now you're getting really high fidelity loads to evaluate that component, and you know that you're getting the appropriate boundary conditions for the system. And here what we see is what happens when you've incorporated that MARC component. If you use the arm as strictly a flex body, a linear flex body that is, and you don't get the plastic deformation, you see that the loads in blue there are not nearly representative of what happens when you have that MARC component and it buckles. And so if you want those high fidelity loads, same would be the case of an engine mount or a bushing. You need to be able to capture the nuances, the real high fidelity details of that component, and this is this example. So the last thing I wanted to point out on the Adams Nonlinear Flex front is, again, what we've attempted to do here is expand, so push the envelope for the dynamicist so that he can do more with, in the automotive context, more than just handling and ride, and he can start looking at durability applications. But this is available within Adams View as well, And it really gives you the added level of fidelity, and you can imagine certain use cases, you need to consider full material, boundary condition, and geometric nonlinearity, and that's something that this technology using SOL 400 as an embedded component accomplishes. And it's very approachable for the Atoms user, because in the Atoms environment, when you create that flexible body, you go to the drop-down list, and instead of selecting M&F, you select BDF, and you start from there. So pretty straightforward. Doesn't require the expertise on the FE side that the Atoms Mark co-simulation does. At the same time, some people might favor the Atoms Mark co-simulation for viscoelastic use cases. So there's some overlap in the use cases, but there's also, in some respects, different persona in mind for the two technologies. So depending on which tools you use and what your preference is, you may opt for either Atoms Mark or Atoms Nonlinear Flex. And so this is the workflow there, pretty straightforward. We don't have to spend too much time on that, but you can post-process the vast majority of results directly within Atoms. And so that's an advantage over having to use two post-processors for Atoms Mark. And then the applications here, twist beam certainly is pictured there. You can also do springs with this technology if appropriate, but component buckling, where you're looking at plastic deformation, is certainly something of interest. And then getting very high resolution again on the mount, similar to with Atoms Mark, it's something that's appropriate for this.